Okay. Good morning, everyone, and welcome to the P and Applied Mathematics seminar. It's a pleasure for me to open session 97 of the seminar. Today we have two excellent speakers, Alberto Corella and Silvia Sastre. Introducing Alberto Corella, we have the Professor Ana Dubova. Thank you, Ana. You can start.
Okay, thank you, Juan. Thank you, Alberto, for being with us. So I will say some words presenting you. So Alberto Domínguez Corella studied at the University of Sonora in Mexico, and he did his PhD at the Vienna School of Mathematics, a joint postdoc between Technical University of Vienna and the University of Vienna. He was at the University of Erlangen-Nuremberg in Germany as a postdoc, and now at the Sorbonne Institute of the Mathématiques de Jussieu. He won the Best Paper Award of Mathematical Department of the Technical University of Vienna in 2022 and obtained a Humboldt Fellowship last year. So today he will give a talk entitled Random Domain Decomposition for Parabolic Optimal Control Problems. So please, welcome, you can start.
Thank you very much for the introduction. I'm very happy to give this talk. Well, the concept of the talk is to show a numerical scheme to solve parabolic equations. And the way I will proceed will be through example. I will take some very basic example, and I will try to make the talk elementary and not get into technical details. Well, I would like to start in common ground. Maybe all of us know what gradient descent is. Gradient descent is a numerical, an algorithm to find minimizers. In general, it does not find minimizers. It finds critical points of smooth functions. And the way it works is very simple. It chooses a point, which is can be randomly chosen, can be any point, and then the gradient is calculated at that point. Minus the gradient represents the steepest descent direction. So when looking for a minimum, ideally what one wants is to go in a descent direction. And infinitesimally, the gradient, minus the gradient, gives the steepest one. So it's a good choice to go. So the algorithm is simple. The next point will be calculated as the original point, moving with a little step in the direction of the minus the gradient, which is represented in this formula. It seems very simple, but most of the implementations seen nowadays are based on some type of gradient descent algorithm. Well, of course, there are many variants of it. It can be chosen to be implicit. So, like in this formulation where the equation has to be solved. And of course, one may think, what is the thing here? There is a parameter appearing in gradient descent. If this parameter is very small, one can easily imagine that the minimum will be found at some point, that it always decreases and it's never too far. But in practice, if the parameter is very small, it will take a lot of time to find the minimizer. And this is not convenient for numerical purposes. Hence, I can say that gradient descent is still a research area ongoing, because there are many criteria to find which should be this parameter. There are many criteria to choose it in different contexts. So if it's too big, the algorithm will be quicker. but one risks that it will stop following the minimizer, or at least the critical point. If it's too small, it's very sure that it will be descending the sequence generated, but then it might take forever to descend. There is some concept which has become popular in recent years, which is gradient flow, which is actually a very old concept. And one can think of gradient flow as the infinitesimal trajectory. The gradient descent sequence generates a discrete trajectory. And the gradient flow, it's like the limit trajectory when we make this parameter smaller, smaller, and smaller. And actually, even for quadratic functions, when you consider the gradient flow, you realize that these gradient flows are just linear equations. And they reach the minimizer, but they reach it in infinite time. The solutions of linear problems are like exponentials. And it takes the whole interval to find the minimizer. So this gives us intuition on why this parameter in practice shouldn't be very small. Okay. Of course, if you do implicit gradient descent, I mean, in practice, this is more robust because you can ensure that it's always minimizing, even if the parameter it's bigger, especially for convex functions. Convex functions are the best type of functions for the people who do optimization. These functions have the particularity that all critical points are minimizers, which is highly convenient when you have an algorithm that only finds critical points and you want to find minimizers. All right. Let us try to get into some more modern topic, which is stochastic gradient descent. Though this was originally formulated in 1950, it became very, extremely popular in the last 20 years. And this is due to the following fact. Stochastic gradient descent, it's much faster than regular gradient descent. And in machine learning, deep learning, all these things that end with learning, what they do is to optimize a function that depends on data. And when they formulate this function, well, they have to find the minimizer. And how do they do it? Well, a breakthrough that came in recent years was backpropagation that helps to find the gradient of these functions. So what they do is gradient descent, but they have so many data that it would take forever to calculate full gradients. So what do? They do stochastic gradient descent, and this is faster, and this has marked the path. This was a huge breakthrough, all these things together that make deep learning, neural networks, and all this stuff possible nowadays. Even ChatGPT that works with a specific architecture called transformers uses some type of stochastic gradient descent. So this is very important in modern mathematics. Okay, and what is stochastic gradient descent? Well, stochastic gradient descent, I will try to explain in symbols. Consider a function, phi, and a decomposition of this function as a sum. Here I have written it as an average of functions. And now imagine that when you do stochastic gradient descent, each time you update your sequence, instead of going in the direction of steepest descent, that would be the full gradient, you take just one of the gradients of these functions that you chose to represent the whole function. In practice, the functions you want to optimize are regressions. So they are a sum of the norm of some other function, the distance from some function to the the data that you want to fit. So you find these representations quite often. So the idea is very simple. Instead, every step, instead of putting the full gradient, put a part of the gradient. But which one? Of course, which one? Well, choose randomly. This is the basic idea of stochastic gradient descent. Just choose any of them randomly. Of course, one can have many variants of stochastic gradient descent, explicit, implicit. I mean, you can add more things, coordinate descent and stuff. Of course, if you have convex functions, it's even better because you can transform the problem of finding a minimizer of a convex function to the one of finding a minimizer of a strongly convex function. Due to the, if you do implicit gradient descent, this transforms into the proximal sequences, which is convenient for some purposes. Of course, and at the beginning of the talk, I said I was going to talk about parabolic equations. And where are the parabolic equations? This is an algorithm to find minimizers of functionals. Well, the heat equation can be seen as a gradient flow, as the heat flow. And a way to see this representation is using convex analysis. You can define the following potential, which is just the H1 energy. And if you consider the topology of L2 and instead of the one on H1 and penalize when the functions are not in H1, you can take the convex of differential and prove that the convex of differential should be single valued for those functions in H1, such that the Laplacian is in L2, and that it should be equal to minus Laplacian. Sorry. Yes. What is this saying? More or less, this is saying the following. The gradient of this functional is minus Laplacian. So if we remember what gradient flow is the derivative equals to the gradient, to minus the gradient, sorry, because it's the steepest descent. So this basically means derivative of a function in time equals to minus the gradient, which is minus Laplacian. So that means derivative of time equals to Laplacian, which is a parabolic equation. Yes, and of course, you don't want to find the minimizer of this potential because you already know the minimizer. The minimizer is 0. And stochastic gradient descent works to find minimizers. So, but we will see that is useful. A way to find a partition to apply stochastic gradient descent is to represent the function, the potential, the H1 energy, as the sum of integrals which let's say you take a partition of the domain, you make a decomposition of the domain, and you represent the integral of the square gradient as the sum of integrals in these subdomains. And you use the partition on unity to have some time to not break, to have a smooth break of this. If you do this, you can check that the subdifferentials are given by some minus the divergence of the partition of unity. Important is that partition of unities are 0 outside the support, sorry, outside the domain. Their support is contained in the particular subdomain. So you already see the idea. If you do something like a stochastic gradient descent to this potential, in each step, instead of having to calculate over the full domain, the Laplacian of the domain, you only have to calculate some type of Laplacian over the subdomain, which can sound harder if you are an analyst, but if you discretize this, you will see a lot of zeros, and this is good for numerical analysis. You will see a sparse problem. All right, and how do you take this partition of unities? Well, I mean, there are many ways, and this is maybe not so easy in practice unless you know very well your problem. Here I have an example of a partition. I forgot to mention, the partitions should be overlapping. Because, you know, if it's not overlapping, maybe the information cannot pass in the next step. This is classic problem. All right. Before I said that for complex functions, implicit stochastic gradient descent was equivalent to this formulation, that the proximal, the next step, the next point in the iteration minimizes a perturbed functional. So since the potential for the heat flow is convex, you can also do this. And you see here, the idea is very simple now. Instead of putting the full potential in this formula, you just put a randomly selected potential and then construct a piecewise function from each one of these steps. We know that if it weren't stochastic, then this piecewise constructed sequence would converge to the gradient flow. We more or less, our intuition about the stochastic gradient descent can tell us that if you take this sequence and you make a function, maybe when the time goes to infinity, this function will reach the minimum. But this is not what we want, really. So a more important question is, if I do some random trajectory, is this trajectory close enough to the original trajectory? This is a different paradigm from stochastic gradient descent, because stochastic gradient descent only says that in expectation, minimizers will be close. Of course, I mean, you can see, you can also see it in a very simple way. You take the time discretization, finite differences, and what you get is this system of equations, where instead of having the Laplacian, you have the divergence of a partition, of a randomly selected partition of unity. Right? Of course, when you discretize, you will see there will be a lot of zeros in this term. So this is essentially, this is what we want, to make the calculation of the parabolic problem or of the heat equation very fast. Of course, you will get a degenerate equation, and these are bad for the people who do analysis, but not for the people who do numerical analysis necessarily. And we expect that it goes much faster with these degenerate equations in each step. And you may wonder, there are many techniques to solve evolution equations. Why do we want to solve it faster? And the answer is optimal control. In optimal control, you have to calculate the adjoint equation. And every time you calculate the adjoint equation, you have to take a lot of steps. You know, you have to, in the numerics, each time you calculate the gradient, it's basically to calculate the adjoint, which is a parabolic equation. You have to do it a lot. Even in paradigms like model predictive control, you have to, every time you have to change it, that you change the data, you have to calculate, again, a full solution to only use a part of it. So this is why one would be interested in calculating evolution equations much faster, even if not so accurate. All right. I will now show a numerical example, but I think instead of showing the parabolic equation, it's much more intuitive to see the obstacle problem, because, you know, the obstacle problem consists of putting a thin layer surface and then an obstacle. And then this thin layer is left under the action of gravity and then falls, and it falls under the obstacle. And it's the obstacle because it cannot pass the obstacle. Okay, the abstract formulation and the potential for this is the H1 energy restricted to the set of functions that are above this obstacle here. And if you think of this domain decomposition scheme, one can think of like making a decomposition and letting the gravity act randomly at each step. Here is some diagrams, but I prefer to show you the animation, which I hope I can share. So apparently I cannot. Can anyone confirm if it's visible?
Yes, it is visible, but we can't see any animation. So just the sequence of
Now?
we see.
Well,
no, we just see a sequence of images. So
it's okay, it's okay.
you have one image which is fixed, and then you have on the left hand side. We can
Yes.
see images. Okay.
All right. On the left-hand side, you will see the deterministic solution of the obstacle problem. And in the right-hand side, you will be this algorithm which chooses randomly between subdomains. There are four subdomains chosen here. And you see, we make one step and the gravity falls in the left side of the graph. If we continue this, we see that on the right-hand side, everything falls uniformly, smoothly. But on the right-hand side, only one piece falls at a time. So it's like gravity is randomly acting at each step of time. But the idea is that the trajectory will look the same overall, even if it's the smaller the steps are, the trajectory will look more and more the same to the original trajectory. You can see it here. So maybe at the beginning it looks like a little bit different because it's falling different, but this random falling under the eyes of expectation will be very similar to the original falling of gravity. All right, let me come back to the screen. Here. All right. So now the idea is simple then. We want to say that doing this stochastic gradient descent type of scheme, we can calculate it and it will look like the original solution. Correct. And as I mentioned before, the idea to do this is to use it in optimal control. Here I put some simple example of optimal control problem, which is, let's say you are given some data in the lab, and then you want to be to a temperature, and you want to find some distributed control that is very close to this temperature given, and you have a control. That's you to do it. One thing you can do is just discretize, right? You discretize everything and put it into the computer. Okay? You can do it implicitly also. But if one follows this discussion, one may think, well, what if I take a partition of unity of the domain in which this PDE is defined, and then calculate this problem, right? In every step of this system, I take a random sequence and a random choice for the subdomains, and then you will create a lot of zeros. So essentially, in practice, this will be all what we discussed before. This will be the final application. But it doesn't look that it will converge because stochastic gradient descent is not made for this. But we actually proved that indeed it will converge, right? One can prove, here is for a linear quadratic problem, but one can increase the nonlinearity of the problem. In general, the results that one can expect is that in expectation, the control generated by this scheme, in which in the Euler scheme, the Laplacian was replaced by these randomly chosen divergences of partitions of unity, the expectation will be very close to the original solution. And this is the error estimate, which is Lipschitz with respect to the h is the discretization parameter. And of course, one thing is that the expectation is very close, but this is not enough because there may be a lot of variance. One can also prove that the variance is controlled by the smallness of this parameter. So if we make this parameter very small, then the solution will be very close. But if we make it very small, again, it will happen what it always happens. If we make the partition very fine, then it will take forever to calculate it. So this is the trade-off in this type of stochastic algorithms. But still it's useful to calculate approximate solutions. For example, one can use it to, maybe one has to do a calculation. Some problem that takes 5 days to compute. And then one, instead of running gradient descent, one can choose to run this type of scheme calculated in a couple of hours. Maybe it's not a solution, it's an approximate, but one can already see if this solution looks like it would be the solution. All right, because if it gives something completely different, one can think, maybe I did some mistake. Maybe it's not worth to run the program for 5 days for something I'm not sure it will go. Okay. So from the analysis point of view, this discretization scheme can also be seen as just solving some PDE constraint optimization problem, which was replaced by a function which is piecewise randomly generated, a type of Markov chain. So one can see this as an stochastic PDE constraint problem, which can be interested from the point of view of analysts. Of course, one may think, okay, this problem that I showed at the beginning was linear, and I showed this problem not to get into the details of nonlinearities. This is a classic problem, but one can also make it more complicated by putting some function which satisfies some properties that I don't want to get, but they are traditional properties. It's nothing very special. Also, one can put nonlinearity in the equation with a classic assumption of that the derivative is non-negative. And one can put box constraints also. Because the original problem I showed had the quadratic term, which makes it much more easy because it locally convexifies the problem. But one can handle, the hard part is to prove that the evolution equations are close. So for this type of algorithms, one can expect the same result, and they're assuming some type of growth condition for the second order form. Here I have the sum of forms, but this is always non-negative. So the classic second order growth condition in L1 is more than enough to get this type of results. So yeah, that is the full conclusion of the talk. You can do a random skip and still get the optimal control. Here you see, for example, the same optimal control, but the Laplacian is replaced by this function. So basically, what we have to do is just replace the original optimal control problem by this, and then discretize this problem according to this mesh. And this will give us an approximation in expectation of the optimal control. I would like to stop here and leave 10 minutes for questions. No. Yeah. So are there any questions about this?
Sorry?
So I would like to finish with this result on the conversions. So are there questions?
Okay, so have you finished your talk? Sorry.
Yeah.
Yeah, so okay.
Yes.
Probably let's ask to the audience if there are any questions. You have a microphone open and you can use also chat. So while people think, and I have a question, have you compared your result with the classical with your classical method of optimization, or finite element method, or finding difference?
Yes. Yes.
Yes. Is it which is the speed of improvement? So how? Yeah.
It depends on your domain. If your domain is very high dimensional, the speed up is huge. But if your domain is just in R2, it's not much. We saw small improvement. But actually, yeah, so actually I should have maybe, but yeah. But if you have a very high dimensional domain, then the improvement will be a lot. But if you want to make it real faster, because if it's a high dimensional domain, it takes a lot of time. Let's say if you have 50 dimensions, it takes forever. But then what you have to do is to take partitions of unity, which are you have to make huge decomposition and just take pieces that you can solve. But if you take a lot, then you lose accuracy, but still you can get approximate solutions. Very similar to what happens in machine learning, that they have huge data, impossible to calculate, and they only calculate small pieces randomly, and that's enough for their purposes.
Okay. Okay, thank you very much. Other questions? So if not, we thank you again for this very nice talk. And okay, Juan, you can
Thank you.
stop the recording.
Ana. Thank you, Ana. Thank you a lot, Professor Alberto Corella, for your amazing talk.